Okay, so today we will be covering some math basics. So going over some linear algebra, a little bit of calc review, and also finishing up some last things from last class's lecture. So you know, the lecture slides are set up for 2 classes a week. And so if you're wondering why you only see 2 sets of lecture slides posted for every 3 classes, that's why. So lectures will be split a little bit. As far as business, Lab 1 is due this Saturday, and as well as the first set of readings. Again, the readings are just completion. If you do readings, pretty simple. Does anyone have any questions on the labs or the readings? Yeah. Probably not. Yes, so if you didn't hear that, yeah, you can display a larger picture by using, I think it's like PLT dot figure with the argument fig size equals something, and you can enlarge the picture. But yeah, it shouldn't be, you probably won't get doc points for, yeah, it's just a smaller size. Okay, yeah, then Slack. Is anyone in here not signed up for Slack or was not able to accept the invite link? Okay, good. So all communication will be on Slack from now on. If you want to talk to me, you have a much better chance of getting a response through Slack than you do through email. Yeah, and then I guess just a couple of shout outs for all these slides. These slides were originally developed by David Wingate, professor in the computer science department. And yeah, I just really want to give some credit to him, and also Stanford CS 231N and Andre Karpathy. But yeah, David Wingate put a ton of work into developing this course, and several professors throughout the years have continued to upgrade it with the latest deep learning research. We're hoping to add a lab this year based on some of the latest and greatest text-to-image models, where you'll get to do some pretty cool text-to-image generation. So yeah, it's a very up-to-date class. As I mentioned last time, there is pretty much, well, I mean, not everything, but all of the most important things in deep learning have been incorporated into this class. So yeah, without further ado, we're going to switch back over to last class's slides. Okay, so this is AlphaFold. This is kind of an intersection with my research. As a review, we were looking at some of the really cool and things that have been good for the world that have come out of deep learning the last couple of years. So AlphaFold came out in 2018. It was a deep learning model designed to predict protein structure. So if you're not familiar with chemistry, as a kind of basic overview, there are these molecules in our bodies called proteins. They're made up of amino acids, which you can imagine as stringing beads of different type on a string. And based on the different types of beads that you put on that string, the string will fold into a very compact structure that will perform a job in our body, like turning glucose into energy or things like that. And so a long-standing problem of the chemistry field has been to predict the 3D coordinates of these folded structures based only on the sequence of beads. And each different type of bead is represented by a different letter. And so a company named DeepMind made its first foray into chemistry by submitting a deep learning neural network trained to predict 3D protein structure. And basically, they blew the competition out of the water. And this is kind of when the chemistry world and a lot of the physical sciences kind of woke up to the potential for using deep learning in their scientific efforts. Yeah, and so the first version of AlphaFold predicted interatomic distances. So if you imagine a grid of length, suppose this string is length L, you imagine a grid L by L and predicting the, at each point in the grid, there's a distance between one of these beads on the string. And they predicted that distance map and also predicted the angles between each of these, they're called dihedral angles between each of these amino acids. And from there, you can kind of reconstruct this structure. And again, they did extremely well. However, they didn't completely solve the protein folding problem. Their accuracy wasn't really up to helpful accuracy for chemistry experimentalists. And so in 2020, they came out with AlphaFold 2, which was much improved neural network architecture that instead of predicting that distance map that I told you about, they predicted the coordinates directly. And you can see these are all of the different submissions to the protein structure prediction competition. And this one on the end is AlphaFold 2. And these scores are based on basically some standard deviations above the mean. So basically, AlphaFold 2, the updated model, is even better. And it's covered up by the video here, but you can see that there's a metric called GDT score. And even experimentally determined protein structures, they get up to about 90 GDT of accuracy. AlphaFold, so then, and this is over time, how groups have performed at different CAS competitions. This was AlphaFold 1, and that's AlphaFold 2. So basically, AlphaFold 2 predicts protein structure as well as experimentalists can determine protein structure with a few caveats, which I won't go into. But basically has become an enormously useful tool for biochemists. And I don't know if you remember last time I mentioned that to experimentally determine a protein structure costs about $20,000 in terms of time for graduate students to crystallize these proteins and run the experiments, as well as money for materials. And now AlphaFold 2 it's freely available. You can actually go and run it on Google Colab, which we use, and you can do it for free. So you can see that's a pretty huge value add for the chemistry world. And I think we will only continue to see this chemistry world be revolutionized by deep learning. Here's another great AI for good application. This is a model that was trained to detect stimulation from nerves and return stimulation in a way that teaches limbs to move again. This is kind of a fun model. I'm not sure if we have a demo, but basically you can translate speech to another language, but in your own voice instead of in some sort of robot voice. So kind of fun. So sci-fi becoming reality. However, there have been some bad applications, and I expect they will only begin to multiply. We're not going to dwell on them for too much time in this lecture, but just a couple of examples. You may have seen deepfakes, which are basically videos designed to look and sound like someone saying something that they did not say in real life. A lot of these models can generate text that is indistinguishable from human writing, which you can imagine being used for fake news and things like that. On even worse ends, involuntary pornography, and in my opinion, some of the greatest concerns are basically artificial intelligence allows you to do things that a human would normally do on a scale that is unprecedented because you now have computers that can do that. And so whether that's screening text messages to prevent certain ideas from being discussed, or implementing systems that block access to your bank account if you are identified in a certain area. There was a story actually coming out of China a couple of months ago where there was a man who wanted to withdraw his money from the bank, and he went to the bank and a surveillance system identified him. And actually, I want to be careful. It may not have been a surveillance system, but I think it was a geolocation system, identified his location and changed his COVID passport from green to red as he got closer to the bank, preventing him from withdrawing his own money and protesting. So you can imagine how these things, this is just kind of the tip of the iceberg of how authoritarian powers can use these things for evil. Yeah, and so just a couple of headlines. Here's a fake news article written about a unicorn discovered in the Andes Mountains. I'll read this in case you can't see in the back. So the prompt is, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And then the rest of this is completed by a model. So the scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned, silver-white unicorns were previously unknown to science. Now, after almost two centuries, the mystery of what sparked this odd phenomenon is finally solved. And it goes on, in text really indistinguishable from what a human might write. So this is.
Given this audio as input.
It's been less than a week since the deadliest mass shooting in American history.
Our method produces the following output.
It's been less than a week since the deadliest mass shooting in American history. And foremost in all of our minds has been the loss, grief felt by the people of Orlando.
So that video was generated completely by artificial intelligence, and other models which are not addressed here are able to generate plausible audio as well. And so you can imagine, the potential that this can be used to, distort what people say, or swing public sentiment for or against a public figure. Here is a case of bias where the algorithms were not trained on a good data set, and as a result, ended up labeling Black people as gorillas. So obviously this is a huge problem, and definitely harmful in propagating stereotypes, or perpetuating stereotypes, and at worst, perpetuating negative stereotypes, and at the most mildest, providing systems that don't work, AI systems that don't work for everyone equally. More news articles. A company that does facial recognition, fined by the UK for scraping citizens' data. An AI company creating taser drones, which you can imagine the just a couple of steps down the road from those technologies. So, and we're going to talk about ethics in a little bit, but on a bit of a lighter note, there are some really fun things out there that have come out as well. So we have music composed by artificial intelligence. We have deep art, where you can take an image and impose an artistic style on that image. This is a model called the Inception model. And basically how this art was generated is they took a trained neural network and they were trying to examine what each of the neurons in the neural network were learning. And basically the way they did that is they changed the input image until a certain neuron was maximized in that network. Does anyone, I don't know if you can see, but this is obviously an image of a nebula, but so they started with an image of a nebula and then modified it until it maximized a certain neuron. Any idea what that neuron might have represented? Yeah, probably a dog or a Cocker Spaniel or something like that. How about this one? Kind of hard to tell, but yeah, some kind of weird fish-looking thing. Yeah, so that's just kind of a fun, like looking inside what a network is learning, and you get some cool art that pops out. That's more in art. This one is a fun game created by a BYU student, actually, Nick Walton. So this is a text-based adventure game run completely by AI, and we're going to give it a try. All right. All right, so we're gonna do this together. So someone want to pick a genre? All right, cyberpunk. What do we want to be? Cop. All right, we're gonna be a cop. Name for a cop in a cyberpunk world? A lot of creativity here today. All right, so right now the language model is being prompted by that scenario, and it just generated this text. So you are RoboCop, a cop living in the futuristic city of Zale. You have a laser pistol and a stunner. You are part of a police unit's tasked with finding government criticizers. This is already taking it. You can see the technical issues. You wake up in the morning and hear on the radio that another criticizer was assassinated last night, leaving you no doubt that your mission is still valid. You drive to the target's location. What do we do?
Yes. Join the resistance.
Join the resistance. You join the resistance.
Easy. I didn't even use the level for him.
You don't know the exact nature of the group opposing the megacorps, but from the briefings you have received, you can only assume that the group's action leads to widespread societal destruction and the elimination of half. The elimination of half. Of the remaining, yeah, the second half of the sentence. All right. So what are we going to do?
rethink their life decisions.
It sounds like it's trying to persuade us that the resistance is a bad thing and that joining was a bad choice.
Rejoin the cops.
Triple H. Find romance with the person you're supposed to kill.
Oh, yeah.
I'm slightly worried. Look for friends. Good question. It can probably handle it just because it's trained on data with misspelled words. The resistance network that exists is fractured and weak. You can find one of the other members of your team here or some of the other members of the resistance. But most are dead or disappeared. All right. So that's just kind of a fun snapshot. If you're interested, you can play around with it some more. But yeah, kind of fun stuff.
What happens if you put in a non sequitur, like just
Try it. Yeah. All right. So another. This is some more recent work that's come out. We mentioned Dolly last time. The latest Dolly is a text-to-image model where you put in text and it generates an image that matches that description. The latest version of diffusion models is called stable diffusion. We're gonna check out a demo right now. So basically, yeah, we can write anything and it will generate an image. So any ideas? That might exist in the training data. So I guess it's the other way around, huh?
Oh, yeah. We do it like you.
Yeah, we can try that. While this is loading, be thinking about another prompt we can put in. Yeah.
I have a question about so artificial intelligence is definitely thrown around a lot, like in like marketing, right, for products. I guess like how many companies do you think actually and this is kind of a big question, how many companies that use artificial intelligence in a way that
Yeah, I mean, that's a great question. So the question was, when companies market AI, what do they really mean? And are they being honest? I would say that most cases probably amount to fancy logistic regression. And yeah, I would say they're in AI in the sense of like C3PO or the Iron Giant or whatever. Those types of AI companies, I would say, are fewer and farther in between than the companies that are training learning algorithms on data. Yeah, no, but that's not to say that AI isn't useful or extremely effective. But yeah, I think it's definitely possible to oversell, and is often done, oversell AI. We're gonna go away from this for a second, let it finish loading. Okay, yeah, so then as an overview, this is the end of the day one presentation, but as an overview of what we'll be looking at throughout this semester, we'll be going over just the very basics of deep neural networks. We will talk about how to train them, how to initialize them, and how to regularize them, how to make sure that that we don't overfit to our training data. We'll talk about classification. We'll talk about convolutional neural networks, which are often used on images. We'll talk about dense image labeling, where instead of trying to classify an entire image, you're trying to classify every pixel of an image. Like you might have remembered last time we saw the image of a driving car, and we had each pixel in that image was labeled as a car or a tree or the road. We'll do a little bit of that. We'll do style transfer, so where we took the image of the woman and her daughter and imposed the style of Starry Night. You'll get a chance to do that. We'll talk about recurrent neural networks, neural machine translation, so using neural networks to translate between languages, generative adversarial models, or GANs, as well as other generative models like diffusion, that's another type of generative model, deep reinforcement learning, and some other topics. So that's what you have to look forward to. We discussed all of this last time. All right, here we go. There you go. Let's make sure we're sharing. So the video lecture can see. So yeah, there we go. That looks like, that one kind of looks like Luke Skywalker. Looks like someone's riding on Luke's shoulders as well. These two got the order wrong, which is kind of interesting. I like how they had to make Luke Skywalker into a child in order to fit on the other shoulders. But there you go. This kind of looks like Dagobah, like the background. So fun stuff. Anyone else want to put in a prompt to run while we continue with class?
B. Okay, purple B.
Purple B?
I don't know.
What else have we got? Interesting. Okay. Yeah. So one thing about these diffusion models is that the more specific you are, the better they tend to be. And so kind of more abstract things like that might be a little more difficult. So yeah, I'm just curious if what else.
Take a whole scripture. Like obviously.
That's a thought. Any suggestions? Let's see.
Can we see what the model will output in language?
Yeah, we can do something like that.
Do a dog playing shuffleboard.
A dog playing shuffleboard.
Underwater.
Underwater. All right. There we go. All right.
Wait, early Picasso or late Picasso? I want to be able to tell what the image is.
Darn. All right, we'll come back to this later. Okay. Oh, there we go. All right, so for this next part of the lecture, we're going to be talking about an intro to some of the math basics of neural networks. Yeah, we'll do quick linear algebra review, talk about cats a little bit, and then talk about how to set up a linear classification problem. So, we got some math. And just as a preface for this, I've had a couple of people reach out to me and ask, you know, I come from a major that's not math or computer science. I'm not sure I'm going to be able to handle the math in this class. And I think today will be kind of a good lecture to see if you're able to really grasp the math associated with the class. And I'll try to kind of start with the ground level understanding of not assuming that you really know anything, to make sure that we're really all on the same page coming into this. So out of curiosity, has anyone in here not taken Calc 3? Okay, so yeah, quite a few. Probably one of the most important things to start out with is understanding what this notation means. So suppose we have a variable x. X can be a single number, so x could be the number 2. But we could also define a different type of object that's not a number. It's a list of numbers called a vector. And so we have a vector of length 5, with 5 numbers in it. And we would say that that vector exists in a different space from x. So if x is a scalar, we would say that x is a real number, or is a member of the set of all real numbers. If x is a vector, if x is 5 numbers, we would say that x is a member of the set of all vectors of length 5. Any questions on that? Pretty simple. Okay, so we now have a notation to kind of describe the length of a set of numbers. And basically all of deep learning amounts to functions that go from vectors to scalars, or single numbers. And so this is another type of notation that I think we may see in a bit. If you have R something to R something else with an arrow in between, that describes a family of functions. And so basically all of the functions that we will deal with in deep learning go from Rn to R. And we'll get into that a little bit more. Yeah, also just kind of an aside, if there's anything that doesn't make sense, especially during this lecture, please raise your hand and ask a question, because chances are you are not the only one having that question. You saw how many people come from a background of not having been exposed to this before. And also one of my goals for this class is that you can look at crazy math notation and learn to not be overwhelmed with it, and kind of break it down piece by piece and know what questions to ask to understand what math is describing. Yeah, and so a couple of other concepts to cover here. If you see something that's not R, you might see something that's that looks like a fancy C. That describes complex numbers. And then n by n would describe, rather than just having a vector, you would have a matrix of dimensions n by n. And a matrix, let me make sure I cover that, is rather than just having a list of numbers, we have a grid of numbers. Yeah, you don't need to worry about those really. You just need to worry about Rn and Rn class. Moving on. We have this thing called a dot product. And a dot product is probably the most important math concept that you can understand for the sake of deep learning. So there is the math definition, which is this. And then there's the intuitive definition, which they don't really teach you when you take linear algebra. But the intuitive definition of a dot product is similarity. If you take a dot product operates on two vectors and combines them into a single number, which will be called a scalar. And if the two vectors are pointing in the same direction, the dot product will be highly positive. If they are perpendicular to each other, the dot product will be 0. And if they are pointing opposite directions, the dot product will be negative. And so you can think of a dot product measuring similarity from exactly the same all the way to exactly opposite. And someone take a look at this equation and explain to me what they think is going on here. Yeah.
Is it saying like, it's saying look at the two vectors, so transpose the first W so they can multiply them, and then when you multiply them together, or on the right is just saying multiply every x minus x.
It was the first one that you said.
Well, that's the left side, the right side.
Yeah. So we have two vectors, and we want to take the dot product between them. We take each entry of those vectors, and we multiply them with each other. So someone tell me what I should write here.
4 plus 10 plus 8.
4 times 1 plus, yeah. Times 2 is 10 plus 18 equals 32. All right, so that's it. That's a dot product. That's how it works in math. Quick review. What is the intuitive definition of a dot product? What does it measure? Similarity. Great. All right. We are going to skip this. On what? Yeah, great question. Yeah, so there is, you can imagine going back, well, I deleted the numbers, but you can imagine that you can make the numbers in those two vectors as large as you want and make that dot product as large as you want. And so a lot of the time, you're getting at an important point, which is that a lot of the time, when you do a dot product, you will shorten both of the vectors to have length 1, and then multiply them by, and then take the dot product between them. And then, then that dot product will be bounded within a circle. That's another proof that we are going to skip. Okay, so now we're getting into what we're actually going to be doing in deep learning. So in deep learning, we often have, we're going to define a neural network that looks like this. The most simple neural network is a one-layer neural network, where you remember a neural network diagram. I'm going to write on the board instead. This is a simple one-layer neural network. And if you remember, each of these lines is assigned a number, which we will call Wi. And you can imagine that we want to make you can make a matrix that describes all of these connections. Put that up so people on both sides of the room can see. So we're going to put each of these numbers into a matrix. In fact, let's put them into this one right here. So the network will take as input a vector which we will call x. And it will be multiplied by a matrix that we will call W. And the dimensions of W will be the number of input nodes, which is 2, by the number of output nodes, which is 3. In this case, we will just make our W this. It will be 2 by 3. And actually, it's going to be reversed. It'll be 3 by 2. And then X will have what dimensions according to our diagram? Exactly. And so we want to put these numbers in this matrix. Can someone tell me where they think these would go? Yeah.
First one goes top left.
What was that?
1 goes in the top left.
Exactly. Yeah.
Below 1.1.
No,
actually 1.2.
Yeah, below is going to be 1.2.
And then 1.4 below that.
Yes. And then as we go across, what will it be?
1.1, 1.3.
And so you can imagine these W numbers in this weight matrix as strengths of connections between different nodes, between each of our input numbers and each of these intermediate neurons. Yeah, so we'll bring this back down. So you can think of this neural network process as a sequence of dot products. And the way this works, if you remember how the way that matrix multiplication works is, and this is from linear algebra, is you take a vector, you transpose it, and multiply each element of that vector with each element of the top row of a matrix. And then you do the same thing for the next row, and then the same thing for the next row. And what that amount, and then once you've multiplied all of those entries together, you sum them up to make a single number. And that might sound familiar from what we were looking at a couple of slides ago when we were looking at dot products. And so in deep learning, we're going to be doing a lot of matrix vector multiplication, which really just amounts to dot products between an input and each row of our matrix. Makes sense? Any questions on that? Yeah.
Remind me why we did 3 by 2 instead of 2 by 3.
What?
Remind me why we did a 2 by 3 or a 3 by 2 instead of a 2 by 3.
Good question. So when we're talking about the dimensions of matrices or vectors, the first number is the number of rows, and the second number is the number of columns. So this would be a this would be a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by a 10 by something, we'll just say 10 by n matrix. And then in order to multiply a matrix and a vector together, they need to have matching the second dimension of the first matrix has to match the first dimension of the second matrix. So in this case, this would be an n by 1 vector. And so we have a 10 by n and an n by 1. And that makes it so that we can multiply these together. In this case, we had 2 inputs, which means that our x had length 1, which meant that the second dimension of our matrix had to have, or sorry, we had 2 inputs, which means x has length 2, which means that the second dimension of the matrix has to have dimension 2. Good? Okay, any other questions? All right. We are out of time, so we will end there. Oh, the dog's playing shuffleboard. Yes. All right, here we go. Dog's playing shuffleboard underwater. Yeah, kind of close. Oh yeah, and a little bit possibly right here. Okay, thanks for coming.